Hi everyone, so today we're going to be doing our solutions for problem set 2. So let's look at the images and find the defects below, state the dimensionality of the defects. Not all defects might not be available. So we know vacancies are 0D defects, so are self-interstitials, so are impurity interstitials, so are substitutional atoms. Edge dislocations are line defects, so that's a 1D defect, grain boundaries are 2D defects, and voids are 3D defects. So let's see if we could find some vacancies. Well, here's a vacancy here, where we have atoms that are missing. Vacancy, 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 vacancy. Excellent, so we got that ticked off the list. Self-interstitials. Self-interstitials are a little bit hard to visualize here. So we have to look for an atom that's basically pushing out or extending other atoms. In a 1D system, especially here, this is kind of more like an alloy system. So finding the self-interstitials are a little bit kind of hard to visualize here. And actually it's going to be really hard to / impossible to kind of to see. Like maybe something over here, but these are more kind of other types of defects. Perhaps right here, but anyways, so it's going to be kind of hard to see this guy. Impurity interstitials, so those can be either smaller or larger. There's lots of impurity interstitials here, so if we assume that these small atoms are our host lattice, this is an impurity interstitial, this is an impurity interstitial, this is an impurity interstitial. Here we actually see a substitutional impurity as well, so you could see tons of those. Edge dislocations, just like we saw in our Bragg bubble wrap video, edge dislocation, edge dislocation, edge dislocation. So lots of edge dislocations. Here's another one, edge dislocation, all throughout this material here. So edge dislocations, grain boundary, we can see quite a few grain boundaries here. Grain boundary continue on here, grain boundary here. You can see an edge dislocation here, an edge dislocation here. But again, the grain boundary is basically defining different angles of atoms. So you can see here in this crystal, the grains are oriented like this, whereas in this crystal, you get this kind of orientation like this. So it's a slight angle change. Same thing here. Same thing here. So we could see kind of this change in angle. So there's this angle between where the crystals are essentially aligned there. And then finally, for a grain boundary, or actually for a void, this could be considered a void, but again, usually for a three-dimensional defect, we're talking about tens of thousands or hundreds of thousands of atoms. So let's move on to number 2. For number 2, I have 3 of my students, and we're calculating the enthalpy of formation for vacancies of Al, which should be 0.6 eV. They each hand in a graph, which one's correct, justify which graph will have lowest concentration of vacancies at any given temperature. So we're going to see that we know that the concentration of vacancies is equal to exponential minus delta H f of formation over kT for metals. So this only holds for metals, and this is a delta HF. So when we take the natural log, let me kind of clear this up a little bit. So when I take the natural log of this function, natural log xv, this disappears. I'm plotting 1 over t. So my slope here, which is what we're going to calculate, is going to be equal, my slope value is equal to minus delta HF divided by k. And I would know that we're working in basically in EV, so I could actually go ahead and let's plot it actually. Let me go ahead. Let's take a peek right here. So I know that my k is equal to 8.617 times 10 to the minus 5. That's my Boltzmann constant in electron volts per k. So that's my k. And now let's go ahead and let's calculate the slope. So I want to take basically the point right here, and I want to take the point right here. So that looks to be about 60-ish. This looks to be about minus 15-ish. So I could go ahead and find that. So my rise over 1 minus, basically, what's my change? Minus minus, so minus 60 minus minus 55, so or plus 15. And then I divide that by my change, which is 0.08 minus 0.02. So that's going to give me this value here. And I'm going to take this, I'm going to solve this, set it equal to, again, my slope is equal to minus delta H delta HF divided by K. And we'll solve. And that looks pretty close. If we look at some other values, for example, this looks to be about like minus 200. Here, this looks to be about kind of close to 1,000. So if we increase that slope value to, let's say, basically minus 1,000 plus 200, that would give me this value, and you'd see our enthalpy of formation explodes. So as our delta HF increases, so the larger our delta HF value, the lower the concentration of those defects. Because again, harder to create those defects. So this will have the lowest concentration of vacancies or defects at any given temperature. All right, let's look at number 3. Write 3 extrinsic reactions incorporating Ta2O5 into my MgO. So we need 3 of these interactions. Tantalum pentoxide into MgO into MgO. One reaction must include a substitutional cation. So I'm going to substitute Ta in for Mg. Mg is 2 plus, Ta is 5 plus, so that's going to lead to a change in 3 plus substitutional cation and cation vacancy. I can only create vacancies in my host. So vacancy number is minus 2, so I'm going to need 3 here, I need 2 here. That's going to leave me 2 there, so I need 5 oxygens plus 5 oxygen, oxygen. X for mass balance, let's see, 2. So we need 5, I need 5 in front of here. Excellent. Another one, cation interstitial. So Ta, I'll put it on the interstitial side, so that's going to be 1, 2, 3, 4, 5. So cation interstitial and a cation vacancy. Again, I can only create vacancies in my host, so I need this to be 5 here, I need this to be 2 here. That's going to leave me again with 5 other oxygens, and I'm going to put a 5 here. And then finally, the last one must include an anion interstitial. So oxygen interstitial, I need a cation vacancy. So a vacancy in my cation, which would be minus 2. And then I also need a cation interstitial. So I need to put basically a Ta cation interstitial. So this is 1, 2, 3, 4, 5. I need to put 2 here. I'm going to go ahead and put, let's see, I'm going to go ahead and do 4 here. So we got 4 oxygens, we have 2 tantalum, so I need 1 more oxygen. And that should give me my charge balance, oxygen, oxygen, X, or mass balance, excuse me. And then if I look at my Mg, O, I'm good to go. So that's my defect reactions. Write the Frankl and Schottky defects for YF3 and FeO23. So let's do Schottky's first. So null goes to vacancy in Y, which is going to be a minus 3 plus 3 vacancies of this, which is going to be positive here. Let's go here. Null goes to vacancy of Fe, vacancy of oxygen, 1, 2. I know there needs to be 3 of these guys. There needs to be minus 3 here, 2 of these. Okay, good to go. For our Frankl defects, again, we're going to have to write it for each, basically, material, for each element. So I'm going to create an interstitial, and I'm going to leave behind a vacancy in Y. And the same thing for F interstitial plus vacancy F. Charge compensating interstitials and vacancies. So Fe, and hopefully you get the picture. Fe, we're going to do minus, or actually plus 3. 1, 2, 3 on an interstitial plus vacancy of Fe, 3. And then finally, let's just get our oxygen in here. So oxygen interstitial, 1, 2, plus vacancy oxygen, 1, 2. So there we go. The enthalpy of formation for Fe2O3 for the Schottky defect is 3 eV. Frankl anion is 4 eV. Frankl cation is 1 eV. What's the dominant reaction? Frankl cation, because the lowest enthalpy of formation. So write 2 possible defects for the incorporation of ZrO2 into indium oxide. So let's go ahead and do that right here. So when we do that, so I need to do ZrO2 into In2O3. So I need to do a substitutional cation. So for 1 ohm, Zr, this is indium, 4 plus, 3 plus, so 1 here. Then I'm going to also add, let's try to scoot it over here so you can see indium oxide. So I'm going to do now plus the vacancy of indium, which is going to leave me a -3. So I'm going to have to put a 3 here. So it's a 3, 6 oxygen, oxygen X. So 3 indium. So I need 2 here. And there we go. ZR2, indium 2, 3. I'm going to put ZR interstitial. That's going to be 1, 2, 3, 4. I'm going to also do add indium 1, 2, 3. So this is going to have to be 3 here, 4 here, 2 here, 3 here, plus 6 oxygen, oxygen X. So there we go. We've got it. 2 defects. Now, oops, let's not rearrange that here. Hopefully that didn't mess up our recording. Draw the Berger circuit for A, B, and C planes for figure 3. Determine which, if any, type of defect is present. So for A, I'm going to choose my tangent vector like this. I'm going to use my starting point here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, or 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8 steps. 1, 2, 3, 4, 5, 6, 7, 8. So no Berger circuit here, no defects. Let's go in this direction. So I'm going to start here. I'm going to go 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm going that specific direction because of the right hand rule. And then we got 1, 2, 3, 4. 1, 2, 3, 4. So starting vector to finish. So that's my vector. My B is anti-parallel to my T, which is right here. So this is a left hand screw. And then finally, I'm going to choose it coming out here. I'm going to choose my starting point here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Start, finish. My Berger's vector is perpendicular to my T tangent here, so that is an edge dislocation. All right, let's get and work on number 7 now. All right, so let's go ahead and do number 7. So I'm investigating the diffusive behavior of 2 Mr. materials. Diffusion couple setup as usual. Short period of time, have the resulting concentration profile below. So we know because B is diffusing more, it has a higher concentration into alpha, that the diffusivity of beta is greater than the diffusivity of alpha. Thus, we know that the flux in the C frame of beta is going to be much larger. Alpha is going to go in this direction, but it's going to be smaller because my diffusivity is proportional, or my flux is proportional to my diffusivity. And then finally, we know that in the C frame, we need the flux of the vacancy in our 2 components to be equal to 0. So the sum of the fluxes must be equal to 0. So that's going to be our vacancies. So what's going to happen in our system here is that our extra half planes that exist here, on this side, they're going to be filled with these red atoms moving in. But on the other side, this is going to lead to expansion. On the other side here, the green is going to gobble up. The vacancies are going to gobble up. These extra half planes are going to disappear. So this material is going to shrink, causing this interface to move this way. And if you leave this for long enough times, long enough temperatures, you'll see pores that start to form on this side because it's diffusing much faster. Again, vacancies are moving the opposite direction. So that essentially answers this question, this question, this question. Again, Kirkendall pores form only at temperatures that are high and at times that are long. Additionally, basically for these other questions, differences between intrinsic and self-diffusivity, calculate velocity of the interface, that's just going to go back to lecture 4 and kind of reading some of these definitions. So you can kind of see this relationship here. You could also calculate the velocity of the interface right here. So this is the velocity of our interface right here. So again, those are just kind of more looking and reading through the note type questions. So the other questions are more important for your exam. All right. So I have titanium nitride is a surface coating that can increase the hardness of my piece of titanium 6 aluminum 4 vanadium. So this is 6 aluminum 4 vanadium. And it is a piece of sheet metal that is 100 micrometers thick. So here my x is equal to 0, here x equals to 100 micrometers. So my sheet metal is this. I want to surface harden it with a layer of nitrogen and that diffusion coefficient. So let's go and pull up Mathematica. So diff ni is equal to 1 times 10 to the minus 16 meters squared per second. So I don't want to work with centimeters, I want meters squared per second. So I apply essentially this nitrogen atmosphere that has a nitrogen concentration. So here my concentration of nitrogen is equal to about 0.1, so weight percent. So I just write it as a fraction. And we're doing this for the time here. T is equal to 1 hour. So plot the concentration nitrogen function time assumptions that we were going to make in solving this problem. So I'm going to solve this PDE, fixed second law, E squared C, just assume this is a one-dimensional problem. My ODE that I'm going to actually solve is dc d eta squared plus 2 eta dc d eta, and then set that equal to 0. And where again eta is equal to x divided by a square root of 4 dt. So let's go ahead and figure out what our boundary conditions were. Because again, this is second order, so I need two boundary conditions. So I need to figure out, okay, well, at what is my concentration of nitrogen at eta equals 0? Again, I'm applying that surface with this kind of constant concentration. So that concentration is going to be simply, it's going to be 0.1 because it's 10 weight percent. What is my concentration of nitrogen at distance of 100 micrometers? Or I'm going to make this assumption using this condition, L is greater than 10 square root T. So let's see, if this is true, then I can make the assumption this is semi-infinite, and then thus the concentration here is 0. But let's go ahead and see if this condition, this assumption, we need to satisfy this condition to assume semi-infinite. So the length of my material is 100 micrometers. So I need to see if 100 times 10 to the minus 6, is this greater than 10 times square root of d times my, or diff nitrogen. And my time is 1 hour. So 1 hour times 60 minutes an hour times 60 seconds per minute. Yes, so it is larger, so I can treat it as semi-infinite. So now I just need to solve my differential equation. So I'm going to do dsolve, and I'm going to do my differential equation. So it's going to be concentration double prime as a function of eta plus 2 times eta times concentration prime as a function of eta. Set that equal to 0. I want to solve it for my boundary conditions, C of eta equal, or C of 0 equals 0.1, and C of infinity, equals, set that equal to 0, and then I'm solving it for C of eta, and for eta. I believe this should work, and there's my, what do you know? That is my concentration profile. And we're also going to say that eta equals x divided by square root of 4 times diff ni times t. So when I do that, I can kind of look at this function here, and now I could do my nice little manipulate plot. I want to plot this function as a function of x goes from 0 to 100 micrometers, 100 times 10 to the minus 6. And then I'm going to want to manipulate this plot. I'm going to look at plot range all. Plot range all. And then close it. And I want to see it from t goes from 1 to, let's see how long this assumption holds. So I want to solve for how long 100 times 10 to the minus 6 equals 10 times the square root of diff nitrogen times t. Oops, solve this up. So it lasts for 1,000,000 seconds, so we'll go up to the million. And let's do it in terms of 1,000. So let's look at my manipulate plot. And this looks pretty correct. Great. So that is pretty much it for that problem. Excellent. So it turns out I actually only need to make sure that my nitrogen penetrates a continuous, basically, front for 2 micrometers thick. So how long will this take? So now I need to use my engineering approximation, which is x equals 2 the square root dt. So my x is 2 micrometers here. So I'm going to go ahead and solve for what is my time to hit that 2 micrometer threshold. So 2 times 10 to the minus 6 equals 2 times square root diffusivity of nitrogen times time, 10,000 seconds. Great. Now, 10. I'm trying to implant a new mystery material into silicon, and you can see a plot of the dopant concentration versus depth into the silicon chip in my figure 5 right here below. And then we're also told that this occurs, the time is in the minutes, so these values here are time, each of these curves in minutes. We're also told that this process occurred at 1000 C, so temperature equals 1000 degrees C. So I'm going to kind of start writing some of these values down. So my temp 1000 C is equal to 1000 plus 273. I want to make sure we're in those units. So let's see what else we got. Estimate the diffusivity of the mystery material. So we need to estimate the diffusivity of the mystery material. So we've given this dopant concentration, so we're going to use this as our implantation depth. But diffusivity, we're going to use this expression, minus QA by KT. So now we're going to basically do something very, very similar. So let's go ahead and we're going to estimate the diffusivity of the material. How long would it take if it was 100? How long would it take to attain the same amount of diffusion if the temperature was 1000 C? So we'll go ahead and look at that, or same how long, same amount of diffusion depth, and then the activation energy is 2 eV. So our QA is equal to 2, and then we know what our K value is from previously, again, for that electron volts, because we're going to be working with electron volts per K here. So how are we going to solve this problem? We know what QA is, we know what T is, we know what K is, we don't know this values, so how are we going to figure out diffusivity? Well, I'm going to take a standard line here and see that after 10 minutes at 1000 C, if I'm looking at this specific dopant concentration, it penetrates 40 nanometers. So let's go ahead and solve. Let's not open up LaTeX. Let's not open up LaTeX. So let's solve that 40 nanometers, 40 times 10 to the minus 9, so that equal to 2 times square root diffusion, actually we don't know, so d mystery times, what's my time here? It's 10 minutes, so times 10 minutes times 60 seconds per minute. So let's go ahead and solve. Let's solve that numerically. So this is the diffusion of my mystery material, the diffusivity capital D. I can now solve for d mist and set that equal to d naught times exponential minus QA divided by K times temp 1000 C. So we're good there. Oops. We're good there. So we've got our D naught. And now we could ask ourselves the question, okay, how long, if we want to figure out the diffusivity at D100 C, it's going to be equal to, basically, all we're going to have to do is plug in D naught times exponential minus QA, that does not change, divided by K times 100 plus 273. So that's my diffusivity there. So to get the same amount of diffusion, so I can solve for when do I get, so 40 times 10, actually I'm going to copy this over here. So how long will it take to get the same amount of diffusion depth? So now D 1000 C, and then I want to figure out what's the time it takes. Oof, that's quite a long time, as you might expect. So appreciate the power of essentially that temperature dependence. All right, so now let's go on and move into problem 11. All right, so let's go ahead and do problem 11. So I'm going to go ahead and draw my kind of standard plot. So we need the log of the concentration. Let's see, natural log ln. So we're interested in Na vacancies. So vacancies of Na, that concentration, it's going to be that versus 1 over T. We know intrinsic over here, extrinsic is over here. And we also want the log of the diffusivity of Na versus 1 over T, intrinsic, extrinsic here. So we have incorporation, this is our impurity, this is our host, activation energy for Schottky, 5 eV versus 7, that's the dominant defect. So for our intrinsic, we have null goes to vacancy of Na plus vacancy Cl. So we know that our K of Schottky is going to be equal to concentration Va over times concentration Cl, and then that is going to be equal to our exponential minus G formation of Schottky over Kt. We know our electroneutrality statement, Vna equals concentration VCl. And we substitute this relationship back in here. So we're going to just end up with, I'm going to kind of write number 4 over here. We're going to end up with Vna squared equals exponential minus G formation of Schottky over Kt. This moves to the bottom here. Once we take the natural log of this guy, this disappears. We're plotting 1 over t. So our slope is just this minus G formation of Schottky, G formation of Schottky over 2k. We know that diffusivity is going to be proportional to concentration vacancies of Na times our hopping parameter times r squared. Oops, let's give you some space here. So let's go ahead and let's kind of move over here. So our diffusivity of Na proportional to concentration Na vacancies times our hopping parameter times r squared times f divided by 2d. This is not dependent on temperature. This is not dependent on temperature. This is not dependent on temperature. Our hopping parameter is though exponential SGM divided by Kt. So when you multiply those together in our diffusivity in the intrinsic, it's just going to add. So minus G formation of Schottky over 2k, minus Gm divided by k. That's it. So now for the extrinsic case. So again, we're still interested in kind of these different types of steps. I'm just going to pause this here. So it's CdCl2 into NaCl. So CdCl2 into NaCl. I need to make sure that I have one of my defects is a vacancy in Na because that's what we're interested in. And I'm also going to do a replacing Na, so that's a charge of +1, and then I'm just going to have a 2Cl, Cl, X, and then a 2 here. Done. There's no rate reaction because this is an intrinsic reaction. My electroneutrality statement here is going to be equal to this, CdNA as such, and that's going to give me a flat slope here in terms of the temperature dependence for my extrinsic reaction. And for diffusivity, exactly the same. This is my only temperature dependent parameter. So, excuse me. So the slope here is going to have a slope. It's going to have a slope, and it's just going to be minus Gm divided by K. So let's go ahead and do something very similar for the next problem, but I'm going to kind of go a little bit quicker. But let's kind of draw our graphs a little bit nicer. Intrinsic, extrinsic, and then again 1 over t, 1 over t. Same here, intrinsic, extrinsic. What is the problem asking us to do? So here we're looking at indium tinoxide. UO2 is doped, so this is our material. So we're looking at indium. So let's go ahead and we are going to look at basically the concentration or log of vacancies of indium, which is going to be a -1, like so. And then the diffusion, natural log of indium. So let's write out dominant defects or Schottky for indium oxide. So let's go ahead and write those out. So we have null goes to vacancy of indium -1, 2, 3 plus vacancy of oxygen 1, 2. So we know that we need 2 here, we need 3 here. So if I look at my rate reaction, then that becomes K Schottky equals my concentration vacancies of indium, which is 3 squared times vacancy of oxygen to the 3rd power. My electroneutrality statement, again, that's going to be equal to G formation of Schottky, as we saw in the last problem. So again, that's equal to, let's write it out explicitly, equals exponential minus G formation of Schottky divided by KT. My electron neutrality statement is going to be vacancies of indium, 3. I'm going to bring this guy to the over on this side is equal to 2. Vacancy of oxygen, so I'm bringing that there. And then now I know that eventually this slope here, because of this, 5, is going to be proportional to minus G formation of Schottky divided by 5K. And that my diffusivity, again, is going to be very similar, but I'm also minus this. So again, it's minus G formation of Schottky divided by 5K minus GM over K. For the extrinsic reaction, we are doping this with UO2. So UO2 into, let me make sure. I believe it's UO2 into IN2O3. Good. So for our extrinsic, UO2 into IN2O3, I definitely need a vacancy of indium. That's 1, 2, 3, plus U replacing indium. So that's going to be a 3 plus to 4 plus positive there. So we'll put a 3 in here. I'll put a 2 in here. Where's our 3 here? So we need a 6 oxygen, oxygen X. 2 skip 3 electron neutrality. So you can see 1, 2, 3. That over there equals UIN. U, basically it's U replacing indium, substitutional cation. And so we know this is flat, and this is going to have minus GM divided by K. That's it. That's how you want to approach these problems. So I skipped a couple math steps there, but I think you all get the picture. So now let's get into some phase diagram problems. So let's look at the titanium silicon phase diagram here. So congruent melting point, congruent melting point, congruent melting point, congruent melting point, and there we go. This here's a eutectoid, eutectic. This is a peritectoid because we're going from actually let's do it. So this plus liquid, this region here, this region plus this region. It's going to be this region here plus liquid, this material here plus liquid, this plus this, this plus this, this plus this, beta plus here. We're going to do beta plus here. This is going to be alpha plus this material, and so forth and so forth. So this plus this plus this, liquid plus this, and then liquid also plus this. So eutectic, this is a peritectoid, beta, alpha to new material here. This is a peritectic. This is also peritectic. This is a eutectic, and those are all the invariant points. Those are all the congruent melting points. Let's do the exact same thing here while we're on a roll. So congruent melting point here. We have a congruent melting point right here. We have a congruent melting point right here. The regions, so this plus this NB at high temperature plus this region here. We have liquid plus this solid again here. We have this solid plus liquid here. We have this solid plus liquid here. We have this solid plus liquid here. We have, let's go ahead, we have this liquid plus this solid here, this solid plus this solid, this solid plus this solid, this solid plus this solid, this solid plus this solid in these regions. So again, hopefully you kind of get the picture. Liquid plus this region right here, et cetera, et cetera, et cetera. So let's get to the cool invariant points. So this is a eutectic right here. This little guy is a eutectoid. We have peritectic, 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 and another eutectic right here. So those are all the invariant points and congruent melting points. So this problem done. 15, we've gotten that. So calculate degrees of freedom for 20 atomic percent silicon and 1000 C. And then what about 80 SB at 800? So let's do, okay, so let's get this guy. So we're calculating degrees of freedom. So let's go back to the problem. So we're looking at 20 atomic percent silicon, 20 atomic percent at 1000 C. So what are my degrees of freedom here? Well, I'm this phase plus this phase. So my Gibbs phase rule is D plus P equals C plus 1 for a binary phase diagram. I know that for all of these problems, D plus 1 is going to be here. So it's my number of phases. In this region, it's 2, so my degrees of freedom is 1. Great. What about 80 and 800? So 80%, this is not, should not be SB, this should be silicon. 80, actually there's a couple typos here. 80 SI. So 80 SI and 800 C. So 80 SI and 800 C. So right here. So again, same thing. My phases here is 2, so my degrees of freedom is equal to 1 because my components are also 2. So here, degrees of freedom is also 1. What about at 80, get 80, but now at 330. So basically 80 and then right here. Well, on this line, I'm simultaneously in this phase, and I'm simultaneously touching the liquid phase as well. So I'm in 2 phases, so my degrees of freedom is also 1. That's it. So let's go ahead and we've answered all those questions. What's the maximum solubility of Ti into Si? So Ti into Si is basically, you can see here, silicon is basically 0. So there's Ti into Si is essentially 0. But Si, adding Si into pure Ti, we can get all the way basically to about right here. So about 1, 2, 3, 4, 5, 6, 7. So Si into Ti is about 7. And this is important because what does this tell us? Well, silicon probably has a large diffusivity, interdiffusivity into Ti than Ti into Si. So it wants to move and penetrate in there more. All right. I have a sample at 10 atomic percent silicon and 1000 C. So let's go ahead and let's mark that up. 10 atomic percent 1000 C, so right here. So the question is asking us for the concentration and fraction of all phases. So we're in a 2-phase region, so I should have a concentration of beta. I should have a concentration of Ti3 Si. So looking at these concentrations, this is going to give me, my beta will give me 3. My Ti3 Si, that's going to give me 1, 2, 3, 4, 5, about 25. And if I want to do the fraction of beta is going to give me, I need to do my Leber rule, so 25 minus 3. And for beta, remember I'm doing the opposite, so it's going to be 25 minus 10, fraction of the other guy. It's going to give me 25 minus 3, and it's going to give me 10 minus 3. That's it. Got it. So let's look at last problem 15. So we labeled all the regions. Let's see, what's the maximum solubility of ND in SB? So again, we could kind of look at the same idea here. So the solubility, so if we look here, this is my solubility. So I've got about ND in SB. That's probably about like 2%. SD in N, or SB, excuse me. SB and ND, it's probably about right here. Let's draw a little bit clearer. 1, 2, 3, probably about 4. So SB has a little bit larger diffusivity than ND, or interdiffusivity to be accurate. Degrees of freedom at 20%, 20 atomic percent SB. So 20 atomic percent SB, and then what's our temperature? 2000. So 20 and 2000. So degrees of freedom plus phases equals 2 plus 1. Remember, my components here are 2 because ND and SB. So my degrees of freedom here are 2. What about 50 SB and 1650? So 50 and 1650 right here. Well, I'm simultaneously this phase, and I'm simultaneously this phase. So D plus phases 2 equals 2 plus 1. So that's going to give me diffusivity of 1. Fantastic. And then finally, I have a sample at 20 atomic percent SB and 1021. So let's go ahead and write that down. So I have 20 atomic percent here and at 1021. So that is going to give me, I'm in a 2-phase region, so I should have some concentration in the liquid phase, and I should have some concentration that is ND5 SB3. So in the liquid phase, I have about, let's say that's 7. And then let's say in the solid phase here, we are about at 39, 38, let's say it's 37-ish approximately. So my fraction in the liquid phase is going to be the opposite, right? So 37 minus 7. So the liquid, even though we're right here, is going to be my 37 minus 20. And the fraction in my solid phase of my ND5 SB3 is going to be equal to, again, my lever rule 37 minus 7. But now we're going to have basically 20 minus 7. So that's it. That is our problem set. So study this well. Good luck on your exam, and I will see you on Monday. Thanks. Have a good one. Bye.